Welcome to the Explainer. Today, we're tackling a totally classic algorithm challenge. It's one of those problems that honestly looks incredibly simple on the surface, but it hides this fantastic lesson about algorithmic efficiency and memory management. We're going to take a solution from a really clunky brute force approach all the way to a sleek, elegant, and optimal design.
Okay, let's dive into this. Here is the core puzzle we're trying to solve today. How do you move all the zeros to the end of an array without using any extra space? Imagine you're handed a list of numbers. Some of them are zeros, some are not. Your ultimate goal is to push every single zero to the very back of that array, but you've got to do it as efficiently as humanly possible.
Now, before we get too crazy, there is a major constraint we absolutely have to follow. We must maintain what's called relative order. This just means that as we're shifting all those zeros to the back, the non-zero elements have to stay in their exact original sequence. We are carefully shifting things around, right? We're not just scrambling the array into chaos.
And this actually highlights a really common trap people fall into. Think about it like this. If your starting array has the numbers 1, 3, and 12 scattered among a bunch of zeros, the valid answer keeps that 1, 3, and 12 in that exact left-to-right sequence. If you try to take a shortcut, like, say, simply sorting the array in descending order, you're going to get 12, 3, 1, and then your zeros. That is totally invalid. The original order of the non-zero numbers is completely wrecked. Because sorting destroys that relative order, it is entirely off the table.
Section 1. The brute force approach. Whenever you face a problem like this, it's actually highly effective to explore your most intuitive gut instinct first. So what's the easiest way to do this? Well, first, we'd simply create a brand new empty array. Second, we'd run a loop over our original array, basically asking each element, hey, are you non-zero? If it is, we sequentially pop it into our new array. Finally, we take the total length, subtract the number of non-zeros we found, and just fill those remaining empty slots at the end of our new array with zeros. It technically works perfectly, and hey, it keeps the relative order intact.
But wait, here is the massive problem. That brute force space complexity, it requires O of n extra memory. By creating that entirely separate array, we're literally eating up a proportional amount of memory. If our input array has 10,000 elements, we suddenly need extra space for 10,000 more. In the world of optimal algorithms, this is heavily frowned upon. It's just too expensive. We've got to do better.
Section 2. The pattern pivot. So let's shift our energy away from creating new arrays. When you're optimizing array operations, there are generally 4 major patterns we pull from: two-pointer, sliding window, prefix sum, and Kadane's algorithm. Now, sliding window, prefix sum, and Kadane's, those are phenomenal when you want to look at continuous subarrays or calculate continuous sums. But that's not what we're doing today.
Listen to this fantastic insight from the source material. It says, whenever we want to play with particular elements, there we go with two-pointer approach, we essentially want to isolate a zero element and a non-zero element so we can swap them. We're playing with particular distinct locations here. So definitively, we are pivoting to the optimal two-pointer strategy. It's exactly the tool for the job.
Section 3. Step-by-step optimization. Let's do a dry run.
We are going to do a visual dry run, kind of like a flipbook animation. Think of our left pointer as the waiting room. It's reserving the exact spot where the next non-zero element should go. The right pointer? That's our scout, running ahead to check if an element is a zero or a non-zero. Let's say our array is 1, 0, 3, 12. Both pointers start right at index 0. The right pointer's scout asks the first element, hey, are you 0 or non-zero? It finds a 1. Since it's a non-zero, it swaps itself with the left pointer, which, in this very first step, just means it swaps with itself. Because a non-zero was successfully placed, the left pointer steps forward to open up a new waiting room spot, and the right scout steps forward to keep searching.
Okay, now both pointers are at index 1, looking at the value 0. The right scout asks, are you 0 or non-zero? The element says, I'm a 0. Because it's a 0, there's absolutely no need to swap. The right pointer simply moves forward to check the next spot. But the left pointer, it stays firmly behind. It holds its place, reserving that exact 0 spot for the next non-zero number it finds down the line.
Now, what's really interesting about this is what happens next. The left pointer is still patiently waiting at index 1, holding that 0 spot. But our right scout has moved up to index 2 and spotted a 3, a non-zero. The left pointer basically says, come here, I have a place for you. And boom, the swap executes. The 3 and the 0 switch places. Our array becomes 1, 3, 0, 12.
Because the left pointer successfully placed that 3, it steps forward to index 2, ready and waiting for the next one. Meanwhile, the right scout increments to index 3 and hits the final non-zero element, which is the 12.
Which brings us to the final state of our dry run. The 12 swaps with the 0 that the left pointer was holding. The left pointer moves up, the right pointer moves out of bounds, and our loop breaks. Look at the result, 1, 3, 12, 0. All the zeros are pushed to the end, the relative order of 1, 3, and 12 is completely preserved, and we did it perfectly in place without creating a single new array. How cool is that?
Section 4. Translating logic to code.
So, we need to take that visual mockup and build the actual coding mechanics required to execute this single-pass logic in a real programming environment. It's actually pretty straightforward. The right pointer is controlled by a standard for loop, so it auto-increments every single time, endlessly scanning the array. Inside that loop, we ask our question, is the right pointer's value non-zero? If yes, we store its value in a temporary variable, swap it with the left pointer's value, and, this is the secret sauce, only then do we manually increment the left pointer. The right scout handles the loop iteration automatically, but the left pointer only moves when a swap confirms a non-zero has been safely placed.
Section 5. Time and space complexity. Take a second and consider the sheer efficiency of what we just built compared to our initial brute force idea. First up, our time complexity remains O of n. Why? Well, because our right pointer started at index 0 and marched straight through to n-1. It traversed the array exactly one single time. Even though the left pointer is in there facilitating swaps, the right pointer's steady forward march means our operation time remains directly proportional to the size of the array. It is incredibly fast.
But here is the massive victory. So the crucial point is that we achieved constant space or O of 1 space complexity. We completely eliminated that heavy secondary array from the brute force approach. We solved the whole thing completely in place using just 2 tiny pointer variables and a temporary swapping variable. This is optimal algorithm design at its absolute finest.
Which brings us to our final question for you. What's the next algorithmic pattern you're going to conquer from your data structures and algorithms sheet? You've just completely leveled up your understanding of the two-pointer technique, turning a memory-heavy brute force idea into a sleek, optimized, single-pass solution. Take this momentum and apply it to your next problem. Keep learning, keep optimizing, and we'll see you in the next explainer.